So here is what happened. In the discrete time case, you get yk equal to cxk. This is after time k. And then after this time k plus 1, you get yk plus 1. So let's take a look at the observer equations very carefully. The observer equation is, I want to estimate the value of the state at this time. All right? So at this time, the system dynamics that's already happening is this. And I'm trying to estimate this. So that means what I do is this is happening very, very tiny little bit after this time. Okay? So after this time, index k plus 1, I want to do this estimator. I want to estimate the state. Now, what we have so far is the basic design is this. This is what we have been using so far. Let's check the signals. At this time, so right here, I have x hat k, right? X hat k was computed here. So at this time, we get xk, we get x hat k, we get yk, and we actually also get y hat k. So I have x hat k, no problem. I also have uk, which is the control input that happened here. So no problem here as well. X hat k, still no problem. Look at this one. At this time, we are using the output y that's one step in the back. We are using the historical output measurement. However, at this time, we already have gone through, we can already measure the output y at k plus 1, right? The time has passed. I already collected the new measurement yk plus 1. That is not used in anywhere in the observer. In other words, this is not using the most recent measurement, and we can potentially improve the design a little bit by trying to incorporate this one into the observer design. So that motivates the state observer with predictor type of form. And to do that, we're gonna introduce some terminology to make things a little bit more convenient. Let's see how we can do better. We're gonna introduce some concept. Because of this minor detail in this time index, we're gonna introduce x hat k plus 1 slash k to indicate the predicted state at k plus 1. So we are still at this time k plus 1 time index, and we are trying to do a state estimate. But slash k means that using information till time k. So x hat k plus 1 slash k means that I'm trying to use whatever that I have before here to do my state estimate. And then as example, this is one form of a state estimate. I'm using only information up to time k. What we want to do is to do better and have a x hat k plus 1 slash k plus 1 using information that is most recent at k plus 1 to do this state estimate. So this is, we're here, we already take the measurements, and then we want to improve the state estimation. So this is corrected x hat using the most recent information that's available. And then this set of indices, this is exactly the same that you will see in Kalman filter. So that's the important concept. Predictor and corrector. And then we talked about the meaning of these time indices over here. The error, the estimation error, is defined as the difference between x and x hat kk. So the estimation error is the difference between your true state and your corrected state estimate. That's how we define this. The design of these is as follows. The predictor form, the predictor k x hat k plus 1 slash k, this is designed this way. This is saying we try to use everything up to here, and then at this time index, what we have, let's add a little bit more of the signals that we have. Right after this, now assuming that we have done this predictor-corrector form earlier, right after this, we already have x hat k slash k. Okay, so here I already try to use whatever that I can to best estimate my state. What a predictor can best try to do is, this is my best estimate so far, right? I've used all the information up to here, and then I'm moving one step further. So I want to design my predictor as, this is what I have the best, and then I'm going to feed it through the system dynamics, a times x hat k slash k plus b u k. So this is the predictor. I'm using, this is just a prediction. There's no correction yet. And I'm using what I have best available to do the prediction. And then the corrector is, I'm trying to improve upon this by integrating the newly available measurement y k plus 1. So I'm improving upon this one. And then the way that I'm going to improve is similar to this concept over here. I'm going to try to use a error term to drive this update. So the error term, this time I'm going to use whatever that I have at k plus 1. After I take this measurement, I have this. So I try to integrate this inside. And then subtract the estimated output. And then this estimated output is, again, using whatever that I have that has in this predictor step. So in the predictor step, this is the best that I can have so far. And then your c times x hat becomes the estimate of the output at k plus 1. You can compare this with this one. You can compare these two set of observer designs, and you can see the difference. The observer with predictor and corrector break this into two steps. And then in the first step, it doesn't use the most updated output. And in the second step, it uses that. So this seems to make sense in this design. But we didn't talk about stability or eigenvalues at all so far, right? In here, we know that the eigenvalues are easy to design. Here, let's take a look at how we should design L. To see that, let's check the aerodynamics, which is, I'm trying to relate the error at time k plus 1 with the error that's at time k. So we compute the difference between these two. Our definition is right here. So update k with k plus 1. We're going to get x k plus 1. This equation subtracts this equation, which is going to equal to axk minus this. So minus this one first, and then minus this one. So minus two things. And this one, it equals to the first equation here. So I'm going to combine the steps a little bit. So it's minus ax hat kk minus buk. So we finish this part. then minus this one, so it's minus L yk plus 1, which is cxk minus cx hat k plus 1 slash k, so it's this one. This is ck plus 1. So yk plus 1 is cxk plus 1 minus cx hat k plus 1k. Okay? Something cancels. This one cancels with this one. And then we have xk minus x hat kk. So we have xk minus x hat kk, which is the arrow signal here. The first 4 terms becomes very easy. The last part over here is also intuitive. So cx hat k, cxk plus 1, this is caxk cbuk minus c times x hat k plus 1 slash k, so it's minus ca x hat kk minus cb uk. And again, in all these observer designs, you can see the input actually doesn't matter. They're going to always cancel with each other. Then you're left with, combining all these, you have another xk minus x hat kk. So the result is going to be a minus lca ek. And then it is very simple. The result is very simple, although the steps is a little bit long. But the result is that the arrow dynamics is governed by this matrix, A minus L times CA. And then we design L, we should design L such that the eigenvalues of this matrix, they are all stable. So that's the design here. Remember, what was the design for L over here? The design for L over here is to place the eigenvalues of A minus LC. The design of L is to place the eigenvalue of this matrix to make them stable. You can see the difference now here, right? There is an extra A in this predictor-corrector form of the observer design. In here, we know that if the system is in observable canonical form, L can be designed very easily. The trade-off of doing this corrector-predictor type of form is that you no longer have that level of numerical simplicity in designing L. So you make the design a little bit more complex, you try to embed more things in here. The design of the gain, of the observer gain, becomes slightly more complicated. So we finished this more formally by treating C tilde as CA, or treating CA as a new C matrix, C tilde. Now if we use C tilde as the new C matrix for this system, then the conditions for arbitrary placement of the eigenvalues is that A C tilde, this new matrix set, is observable. Or in other words, C tilde, if we define this to be C tilde, the condition is that the observability, new observability matrix is C tilde. You construct C tilde A all the way to C tilde A n minus 1. You check the rank of this observability matrix. If it has rank n, then You can place the eigenvalue of this whole thing arbitrarily. So that's the condition. The observability matrix, you can, we just wrote it as C tilde A, all the way down. If you plug in C tilde equals to CA, it becomes this CA all the way down to CA n minus 1 times A. Or in other words, is QD is the original observability matrix times A. That's the new observability matrix. So this mathematically sounds just more complicated in general. But the good news is this. Usually, the A matrix in discrete time systems, this one, usually this is invertible. If the discrete time system is actually using zero order hold discretization method, if we use that, then the A matrix in here is going to be invertible. And then observability is going to be guaranteed if the original system is observable. So that's a piece of good news in the end. Think about this point after class. Why, if you discretize a continuous time system using zero order hold method, the discrete time A matrix will be invertible, non-singular. Think about that. It's not too difficult to see.